Here are solutions to homework set number 6 for ECE 461-661 control systems. The first problem looks at modeling a mass spring system. Find the transfer function from F to X2. Well, the approach we're using in this class is to do a circuit equivalent. First thing I'm going to do is combine these two springs. These are admittances. Admittances in parallel add as the sum of the inverses. So take the inverse I have impedance. Impedances in series add. Take the inverse I have admittance. This together is 1.71 newtons per meter. Now draw the circuit equivalent. What I would do is first, let's shrink this down. I have three different masses. I'll have three different voltage nodes, x1, x2, x3, my earth reference. Draw the masses relative to ground. Between mass 1 and mass 3, I've got a spring of 2. Between 1 and 2, I've got a spring of 1.71. Between 2 and 3, I've got a spring of 5. At node 3, I've got friction to ground, spring to ground, and a force input. To get the direction of the current source, as the force increases, x2 increases. As the current increases, the voltage increases. So that looks right. That's the circuit equivalent. Now write the voltage node equations. That'd be at node 1, all the admittances attached to the node, times the node voltage, minus the admittances between 1 and 2, times x2, minus admittances between 1 and 3, times x3 is 0. Repeat for node 2, repeat for node 3. That's the current to the node. It's on the right-hand side. Now to find the transfer function, solve for the highest derivative. Solve for s squared x1, divide everything by 0.2, solve for s squared x2, solve for s squared x3, and I get my three equations. Now place that in matrix form. So my states are going to be the positions and velocities. The derivative of position is velocity. That's the one on the off diagonal right here. Zero identity. These equations show up in the last three rows. So s squared x1 is minus 18.57 times x1, plus 8.57 times x2, plus 10 times x3, and I'm done. S squared x2 is 3.43 x1, minus 13.43 x2, plus 10 x3, and so on. Here's your A matrix. There's your B matrix. The C matrix, since the output is x2, is pull off the second state, x2. And here's your D matrix. Once I have A, B, C, D, throw them in MATLAB. So here's your A, B, C, D. Throw it in MATLAB as state space, convert to zero poles and gain. That's the transfer function from force to x2. MATLAB actually makes this really easy. What's important is get the equations right. Once I get the transfer function, I can find the step response. Let's just plot it out to 10 seconds. Find the step response, plot t versus y, and there she is, your step response. Problem 2. Repeat for another mass spring system. In this case, I've got three masses. I'll have three voltage nodes. Your x1, x2, x3. Each one has got mass to ground. Mass 1 has spring and friction to ground, spring and friction to mass 2. Mass 2 has spring and friction to mass 3. Mass 3 has a force input. Once I get the circuit equivalent, I'll write the voltage node equations. At node 1, it's all the admittances attached to the node, times x1, minus the admittances between 1 and 2, times x2, is the current to the node. Likewise at node 2, likewise at node 3. To find the transfer function, put it in state space form. Solve for the highest derivative, so s squared x1, bring everybody else right, is this, s squared x2, s squared x3. Now express that in matrix form. So my states are x1, x2, x3. They're derivatives. The derivative of position is velocity. That's what this tells you. Derivative of velocity is acceleration. That's these three equations. So the first one, s squared x1, is minus 0.3 times sx1, minus 25 times x1, plus 0.2 times sx2, plus 10 times x2. second equation, third equation. Here's your A matrix. Here's your B matrix. Here's your C matrix. The output is x3. There's your D matrix. Throw it into MATLAB. Here's A, B, C, D. Just for fun, find the eigenvalues of A. It's stable. This also tells you the settling time will be right around 20 seconds. 4 over 0.02. Throw it in MATLAB in state space form. Find the transfer function as zeros, poles, and gains. There she is. That's the transfer function from force to x3. I can plot the step response. I'm going to go for it to 40 seconds. That's 4 over the slowest pole, the real part. Plot it, and there's your step response. Last problem. If you have a rotational system, same trick, but here I've got gears. So what I would do, I've got 3 inertias, 3 voltage nodes. Draw each one to ground. I've got a torque attached to Q1. I've got spring and friction. Spring in series going to friction. And this is on the wrong side. That goes over here. Okay, correcting that. I've got spring going to friction to ground, going to a gear. That's a 1:3 ratio. Takes you to inertia 2. That's got a spring in series, friction to ground, going to a gear. 1:4 ratio, going to the third inertia, spring to ground. There's your circuit equivalent. Next step is get rid of the gears. So everything in this region is scaled by where I'm going to, divided by where I'm coming from, squared. Everything over here is scaled by where I'm going to, 1, divided by where I'm coming from, 4, 12, squared. So getting rid of the gears, here's the circuit equivalent. Now, write the node equations. So the first node, I have all the admittances attached to the node. 2s squared plus 3 times theta 1 is minus the admittances between nodes. 3 theta 2 is torque. Node 2, everybody attached to the node. 3 plus 0.5s plus 2/9 s squared plus 3/9 theta 2 minus admittances between nodes. 3 theta 1 minus admittances between nodes. 3/9 theta 3 is 0. And finally, at node 3, all the admittances attached to the node times theta 3 minus the admittances between nodes times theta 2 equals 0. Once I get the node equations, solve for the highest derivative, place in state space form. Again, that shows up the last 2 rows, 3 rows. First 3 rows is just the derivative of position, is velocity. That's these guys right here. Here's your A matrix, B matrix. I want to find the transfer function to theta 1. So my C matrix, here's A matrix, eigenvalues just for fun. What this tells you is the settling time is, here's your dominant pole, about 100 seconds. I want to measure the output to theta 1. There's my C matrix. Throw that in MATLAB. Find the transfer function. There she is. For the step response, I'll plot it out to 100 seconds, 4 of the dominant pole. And here's what she looks like. So that was homework set number 6 for ECE 461, 661, Control Systems.